Hey everyone, and welcome to episode 1 of the Pi Files. I'm Moti Mahmoodi. Today, we're diving into the physics of scale. We're going to talk about why it's finally time to ditch those old geometric rules of thumb so we can actually cure those expensive commercial batch failures. Let's get right into it. Picture the scenario. You hit a perfect 95% yield at the 2-liter bench scale. It's a huge win, right? But then, when you move that exact same recipe to a 20,000 liter commercial tank, boom, an unexplained 20% yield drop. What gives? This right here is what we call the wall of confusion. In the lab, everything looks great. So we type up a static PDF report, toss it over the brick wall to the commercial plant, and just cross our fingers that it will work out. But instead, our MSAT engineers end up buried in spreadsheets trying to figure out why a perfectly good recipe just failed. The truth? The chemistry did not change. The biology did not change. The physical environment did. Let's look at where it all starts. The benchtop reactor. This little 2-liter tank is a perfectly mixed, instantaneous utopia. Now, when you add a drop of feed, it mixes literally in milliseconds. The whole environment is totally homogeneous. Let's look at the commercial vessel. This is where things get messy. At 20,000 liters, mixing does not take milliseconds anymore. It takes minutes. This massive volume introduces severe gradients and a highly heterogeneous, chaotic environment. So what really happened during that tech transfer? Your limiting factor abruptly shifted. In the lab, you were limited by reaction kinetics, but in the commercial tank, you're completely limited by transport rates, meaning how fast the fluid actually moves. A perfect biological recipe just is not enough anymore. Inside that massive tank, cells are experiencing a violently uneven reality. Your batch doesn't just fail everywhere all at once. It fails locally. It fails in those stagnant dead zones at the top, and it gets crushed in those intense shear hotspots at the bottom. Now, for decades, we've tried to solve this by simply extending physical dimensions. But fluid dynamics just cannot be scaled like that. Making a tank taller and wider does not mean the fluid inside will behave the same way. Scaling based purely on geometry is basically flying blind. In fact, sticking to geometric similarity is a critical engineering mistake. We rely on these super simple rules of thumb, like trying to keep P over V or impeller tip speed constant. But this approach totally ignores the chaotic reality of commercial fluid dynamics. Why? Because fluid dynamics does not scale linearly. If you try to maintain tip speed, your mixing times will skyrocket and create dead zones. If you try to maintain P over V, you will cause massive localized shear stress. There is no magical math trick to scale geometry without breaking the physical environment. So, how do we actually fix this? We have to introduce the 3 pillars of process metrics, or PMs. Instead of looking at arbitrary pump speeds, we look at what the actual cells feel. That means focusing on EDR, KLA, and tau. Pillar number 1 is energy dissipation rate, or EDR. This completely replaces outdated RPM and tip speed calculations. It gives us the exact mathematical measurement of the physical shear stress and the destructive turbulence that's actually hitting the cell. Next up is Pillar 2, Volumetric Mass Transfer Coefficient, or KLA. This metric cuts right through our assumptions about air pump speeds. It defines the actual physical rate that the oxygen and the vital gases successfully dissolve into the liquid to feed your reaction. And finally, Pillar 3 is macromixing time, or tau. This is the exact wait time for true homogeneity. It forces us to face the physical reality of massive volumes, telling us exactly how many minutes it will take to wipe out those dangerous concentration gradients. When you match the physical environment using these process metrics, you completely eliminate the wall of confusion. By running a digital fit gap analysis to align EDR, KLA, and tau, our MSAT engineers can actually guarantee commercial scale-up success. It's time to put an end to validation anxiety. Let's stop wrangling spreadsheets and start doing real engineering. We can de-risk our tech transfers, secure those high-stakes Stage 2 PPQ batches, and finally build true digital wisdom. Thank you so much for tuning into episode 1. I'll catch you in the next one.